Okay, so we are honored to have Roman back again this week to give the second part of his talk, Types, Gaps, and Pairs of Models of PA.
Okay, thank you, Atar, and thank you all for logging in. This is the second part, uh, and but the talk is really a sequence of well, sometimes connected, sometimes not that well connected parts. So if you missed the first part, I said we will review some material from the first part, but it's not really necessary to have been here uh, uh, last week to follow what I'm going to talk about now. So let me just quickly say what the talk is about. This is what's on this slide. So this is a general theme. Uh, there are various techniques for constructing elementary extensions of models of PA. And once we have a model and its extension, or a model and its elementary submodel, then we want to look at the pair, a model theoretic pair. So this is the first order structure when you have the arithmetic part, and then you have a unary uh, predicate symbol for the submodel. And we're interested what kind of properties of the pair can be expressed in the first order way in this language. And it's not quite clear what the motivation for it should be. It's a general model theoretic question, but as you will quickly see that it's a very difficult task to do anything at a large level of generality, because there's a great diversity among those pairs, and they are not really classifiable in any reasonable sense. But the work here was started 40 years ago by Craig Smorinsky, who wrote a series of papers. And essentially, the way things went, that there are certain techniques, certain tools. You approach the question with the tools you have, and you just see what can be done, what kind of models can be constructed, how many different models, how many non-isomorphic models, how many models that are non-isomorphic but could be elementary equivalent, and so on. And so there is much that can be done, but it's essentially a survey of various ways of constructing those, either elementary extensions or elementary submodels. So I had this list last time. It's a little modified this time. So this is the very short history of the subject. So there were those three papers of Craig Smorinsky from 1981 and 1982, and this is what I said. Here's a number of results pertaining to this very general questions, but narrowed down to the case of countable recursively saturated models and certain isomorphism invariants for those either extensions or pairs when you look at it either as an extension or a submodel. And, and then in the meantime, there were other results in the literature here and there that somehow can be used to say a little bit more about this general area. But formally, two papers that already published 8 years ago. One is Jim's paper on elementary cuts in saturated models, and our joint paper on cofinal submodels, where the goal of this paper on cofinal submodels was to consider some questions that Smorinsky asked, and try to make some progress. And as you will see, well, we've made some progress, but still there is much that probably can be done. And that's why I decided to, maybe it wouldn't be a bad idea to give this talk here at MOPA. So maybe someone will get interested, and maybe something more will be done. So look, so in general, the main theme here will be isomorphism types and first order theories of a model and its cofinal submodel. But those things are all interrelated. And in particular, Jim's paper is about elementary cuts. It's about cuts, elementary submodels that are initial segments, and not in the case of countable recursively saturated models, but in the case of saturated models, which turn out to be, with some hard work that Jim did in that paper, much more tractable than the recursively desaturated case. Questions that are open in the recursively desaturated case are already decided in this case. So I would begin with a brief overview of what Jim did in his paper. Okay, so this is part two, saturated model, and it's all, if there are no credits given to results, then it means it all comes from Jim's paper. And this is something that we already discussed last week. This is one of the great tools that we have are Geismann's minimal types, or they also can be called indiscernible types. They have wonderful properties. So in particular, there is a construction of a tree, a perfect tree of those types. For each subset of omega, there is one of those types. And with the following properties that if the types corresponding to different sets of natural numbers are independent, there is an original definition of what independence means here, but for us it simply means that those types cannot be realized in the same gap of any model. And the connection to recursive saturation is that if the set I is in the standard system of the model, then the type is realized. So as a corollary, each countable recursively saturated model realizes countably many mutually independent minimal types. But if we move to a saturated model has full standard system. So that means that all those independent types, continuum many types, are realized in a saturated model as well. And this will be useful because those types were used to show that if you look at these pairs, a model and a supremum of a gap, and I will recall what gaps are in a moment, and we'll see what it looks like in the picture. But so these are models and their elementary cuts with the largest gap in it. So these are so-called short elementary submodels. So what happens here, you take essentially the same thing is you take an element, you take a column closure of the element in the model, and then supremum closes this all under initial segment. So these are elementary, the elementary cuts, short models. They are themselves not recursively saturated. And with some work, one can show that whenever you take elements realizing different minimal types, Pi and Pj, then these structures are not elementary equivalent. So in particular, we have examples of continuum many theories of these pairs. Okay, so something, but this is very specialized. This is sort of very specialized to this very particular situation, to those very specific cuts. And already gives you a great variety of theories, but we understand exactly what those theories are, where the difference comes. Sorry? Okay. Look, so this is the picture. Really, it says the same thing that I said on the last on the previous slide, but pictorially. So this is your model M. It's a saturated model now, and or recursively saturated. And it doesn't really matter if you're in countable recursively saturated case or the saturated case. You have elements realizing those distinct minimal types. You have gaps around them, and the gap is this largest convex subset of a model that doesn't contain any elementary cuts. So there are no elementary cuts between the infimum and supremum of the cut of the gap. And so Ki and Kj, this should be Kj. These are short elementary submodels of M, and the pairs are not elementary equivalent. But what I also want to add here, that there is this notion of this is cofinality, but not set theoretic cofinality. This is arithmetic cofinality. I defined it before. And it's, again, this is a property of a cut that's defined in the first order way in the pair. So that will play a role. That these particular cuts, they all have cofinality omega, arithmetic cofinality omega in the model M. Okay, so this was the case of shortcuts, and we also have co-shortcuts. So this is the same picture, the same element A, and well, not the same, some element A and some element B, and gaps around them. But now instead of looking over the gaps, you look at the infima, and again by very similar arguments, those things on the left, this LA and LB, the infimum of the gap of A and infimum of the gap of B, they're all elementary cuts, but they are called co-short because they have the least gap above them. Shortcuts have the largest gap in them, and those co-short cuts have the smallest gap above them. And again, they have arithmetic cofinality omega. And by a result from a paper of myself and Henryk Kotlarski, we showed that actually this is dramatically different. That pairs, all those pairs are elementarily equivalent. This is done by playing a certain Barenfoy-Fraser game for these structures. And it's even more general. What really matters here, what established this elementary equivalence between pairs is that that both LA and LB are what we call downward omega coded. They're infima of coded sequences, decreasing coded sequences, coded omega sequences, and that's enough to establish this elementary equivalence. So on short case, we get continue many different theories because the pair realizes the highest, the largest, and the theory can recognize the types of elements realized in it, some of them, but the Koshort case is dramatically different. Nothing gets recognized. All those pairs look the same from the point of view of the first order theories. So this was what we did in the case of recursively saturated models, and it also works for saturated models with the same arguments. So now we change our assumptions. So M is no longer countable and recursively saturated. Is a kappa saturated model of PA of cardinality kappa. Okay, and now we're looking at cuts. We'll be interested in elementary cuts, but this applies to any cuts. There are three types of cuts in a saturated model. Kappa here is the cardinality of the model. So, and they are determined by cofinality, but now this is set theoretic cofinality. So M is an ordered structure. There is a naturally defined notion of cofinality in the ordered set. So a cut is balanced if its upward cofinality and downward cofinality are the same and equal to kappa. And the cut is unbalanced if one of those cofinality is lower. And these are the only three possible cases because of saturation. You cannot have cofinalities, smaller cofinalities upward and downward, because then by saturation you would squeeze some element in between them. So K wouldn't be a cut. So these are only the three cases that we'll be considering. And I will be sometimes saying that the cut is balanced or unbalanced, and sometimes it's convenient to say that the pair is balanced or unbalanced. So I'll be that will mean exactly the same. Okay, and here lambda is any cardinal less than kappa. Okay, so this is what I just said, and that there are those three types of cuts: kappa cuts, balanced ones, and kappa lambda and lambda kappa. But those cardinals represent upward cofinality and downward cofinality of the cut. And from what I said before about those continue many non-elementarily equivalent pairs in the countable case, it follows immediately that there are many theories of balanced pairs, of those kappa pairs. And how does it follow? Well, there are continuum many theories of those pairs of the form M and supremum of a gap. But now for each of those theories, we take a model MK kappa saturated. If there is a model of PA that's kappa saturated for a given kappa, then there will be also a kappa saturated pair MK for the same theory, for the theory T. And because the pair is saturated, it has to be of the type kappa kappa. That's easy to see. So these are the examples. You get those continuum many different cuts. And so so Jim solved almost everything about the saturated case, but something that remains open, which is somewhat intriguing. Look, kappa can be large. This can be an immensely large cardinal. And we're not talking, well, we get non-isomorphic pairs because we get non-elementarily equivalent pairs. And the maximum you can get is continuum many. But the question is, can we get more non-isomorphic kappa than continuum many? And this is open. And despite some effort, even at some point, I asked Shala what he thought about this question, and he was interested. and thought about this for a while, but then decided that's how one would really have to sort of think more about the arithmetic context of it, and it's still open. Look, and if you feel like asking a question at any point, please do so, or write it in the chat. It would be very, very helpful. As I said last time, I enjoy those seminars very much when I listen to them, but talking to one's own slides is kind of weird. Okay, so questions, please. All right, so this was the case of the balanced cuts, and now for unbalanced, well, Jim proved several results. So here is one, and some results are more or less straightforward, and so we're looking at those unbalanced cuts, and there are some criteria for isomorphism of pairs. So the short case, so if both K and L are short, and that means that they are suprema of gaps. Okay? Each of them has the largest gap in it. So, and if the H is the collection of complete types realized in the gap. If the types realized in the type gamma is exactly the same are exactly the same as the types realized in gamma prime, well, that clearly you get isomorphic pairs. And co-short case the same, but now in the co-short case, you have L and K infima of gamma and gamma prime. So there is the smallest gap above both those cuts. Okay, and then, so that's straightforward. What's a little less straightforward, but also follows from standard arguments, that if both K and L are tall, and tall means they are not short. So they are not a closure on the initial segment of a short model, of a column closure of a single element. So, and if they have the same set theoretic cofinality, then they are isomorphic, and the same for the tall case. That there is no least gap above the cut, and the downward cofinality are the same. And that's all standard, and then it's not difficult to see. But more interesting things are happening.
In the previous slide, equivalence meant elementary equivalence?
No, this Google here means yes.
Isomorphism. Okay, thank you.
Yes. Three straight lines would be elementary equivalence. This is isomorphism.
Thank you.
Okay, so what matters in recognizing theories of pairs, it always helps you can define omega in a pair. And we could do it in some case in the countable recursively desaturated case for certain cuts. And here it's actually a little surprising, but easy to see that omega is defined in any unbalanced pair, regardless of how large the relation between lambda and kappa. And this is a argument for the lambda kappa case. The kappa lambda case is very similar. So here is the definition of omega. It says that you talk about all possible B's that code a sequence of length at least n. So it simply says that it says that in K there is an upper bound for any sequence of length n. So when n is standard, clearly, because K is closed under successor, such bound always exists because we're talking about finite sequences. But conversely, we assume that this is a lambda kappa cut. So that means that there is a sequence of length lambda that's cofinal in K. So now you simply consider the type that says this. There is an element such that for every C alpha here from the sequence, there is some index of the sequence that's less than A, such that the ith term of the sequence is C alpha. And again, this is clearly a finally realizable type in the model, and by kappa saturation it's realized, and any B that realizes the type is a witness that if A is non-standard, then this part of the statement is false. So that's simple. Omega is definable without parameters. And because of that, so you can recognize first order theories of certain kind of cuts. So based on definability of omega, is that if you have any unbalanced pair or any unbalanced cut here, so there are those sentences that they can recognize whether the cofinality of K in M is, but here we're talking about set theoretic cofinalities. Okay, the cofinality is omega or Aleph 0, cofinality, downward cofinality Aleph 0, and there is a sentence that recognizes when a model is short, has the largest gap. But like in the countable recursively desaturated case, there is no analog for the co-short case. In the other direction, if both models have downward cofinality Aleph 0, then they're elementarily equivalent, and it follows by the same arguments that are used in recursively desaturated case. Well, saturated models are recursively saturated, and all the same arguments apply. So these are the kind of things that can be recognized by the theory. But what is much more intriguing here, because the previous slide was about the situation, what happens when you have those models of either, kappa lambda, where lambda is, or kappa lambda or lambda kappa when lambda is Aleph 0. But what happens if all those cofinalities are uncountable? And it's interesting that all those unbalanced pairs share exactly the same theory. And it is a difficult theorem. It is a very beautiful theorem. I have been trying to prove or disprove it, and I couldn't. Then Jim wrote some arguments that I also couldn't understand. But then finally, it turns out that you have to get to a higher level of generality, and then the proof becomes something that one can actually complete. And this is by proving something stronger. And in Jim's paper, it's even the statement is even more general, but here I just have a statement for cuts in this one model M. And you look at two cuts, K and L, and you have this lambda, that's the smallest of those cofinalities here. And then it turns out that these pairs are elementarily equivalent, not just for first order elementarily equivalent, but for this Ehrenfeucht-Fresser game setup, when now you play games of length lambda for these structures. So it's a stronger infinitary logic in which they're elementarily equivalent. So it's a beautiful theorem, and there is some mystery here, which I don't know how mysterious that mystery is, but if all these unbalanced cuts, they share the same theory, I would like to know what this theory is. Can it be axiomatized? What kind of, how can we recognize that this is this theory and not some other theory? And I think it's somewhat open. Jim, are you there? Okay. So we don't know whether Jim is there.
I am here.
Maybe he's still there.
Yes.
Right.
Yes, I don't know anything about
So
that.
would you,
Nothing. I have nothing to say.
but would you agree?
Nothing more.
But would you agree?
Yeah.
Right, and neither have I. But would you agree that this is something to give some thought to?
I'm sorry, say it again.
Would you agree that this is an interesting question?
Oh, yes, definitely. Yes. Yes, it seems odd
All
that
right.
there is this theory and we don't know what it is. Yeah.
Right. Exactly. And it's this abundance of cuts, and we all share the same theory, and so maybe this needs some more thought. So there's more in Jim's paper, and if you haven't seen it, I strongly recommend that you do. This is in the Notre Dame Journal of Formal Logic, and there are some other interesting results in it. So it's really a very nice paper. Okay, so now back to the countable recursively desaturated case, and so I said with some combinatorics. So because when we talk about theories of pairs, well, all those combinatorial principles that were studied, in the 80s, starting from Kirby and Paris, and then this whole development of combinatorics inside a non-standard model of Peano, and can actually has done much work in this area, and all those definitions of various combinatorial properties of a cut inside the model of PA, they're all first order definitions. So this is something that a pair, a model and a cut have. So so there's this hierarchy, and now these days there's more than that can be said. Well, Leszek Kołodziejczyk, when he gave a talk there, the Ramsey theorems, infinite Ramsey theorems fit into this hierarchy somewhere. When Lawrence gave his talk, there is something that he used in relation to cofinal extensions of models of fragments. But I will just be talking about those very standard combinatorial properties. So there is semiregularity, and I defined it last time, but I don't really have to, because there are these very nice characterizations of these various properties. So semiregularity simply means that if you look at the model, and this is the collection of subsets of I that are coded in M. So these are traces of coded subsets or bounded definable subset of M traces on I. And if this is a model of second order arithmetic, and if this satisfies I sigma 1 in the language here, that's equivalent to semiregularity. And then the hierarchy goes up. Sigma 2 collection corresponds to regularity of the cut. And then you can go up. I will say a little bit about it in a moment. And then it culminates almost in there are other things that you can put here, but there is the strength. An initial segment is strong if this second order structure is a model of ACE0 arithmetic comprehension. Okay, and then there are other things that you can say. You can separate these various. You know, this is what's here stands for those dot 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 here. There's more that can be said in general about this situation. Which countable models have elementary extensions that satisfy these fragments, either induction and not collection, or collection not induction. And there are still some open problems about it. And there are some conjectures. Jim has a paper when he has some results about it. Canavy proved something about it. But there is a simple argument that can be used in a case of recursive desaturated models that shows that any countable recursive desaturated model M has those cuts, K and L, such that K satisfies induction at the level N and not collection at the next level, and L has collection but not induction. So this adds to this hierarchy of theories that are here. Okay, so I will just say a little bit about what's going on, and the main thing is this: that going back to Smorinsky's techniques of constructing different pairs with different theories or pairs with different isomorphism types, there are two ends at which we can actually do something. And one is below semiregularity. If a cut is not semiregular, there are all kinds of things we can do, and I will show you what can be done. And then if a cut is strong, and I will be talking about elementary cuts, if a elementary cut is strong, there are also other things that can be done that produce this diversity of pairs. But it's absolutely open, or almost open, what happens in between, what kind of model theoretic properties of pairs with those other combinatorial properties. So the first thing is that there is some sort of uniformity below I sigma 1. Below I sigma 1, that means not semi-regular. So examples of those not semi-regular cuts, elementary cuts, are given by what I defined as elements code ascending sequences of gaps. So you talk about elements D that code infinite sequences. So this is C, this is the nth term of sequence coded by C. And to be a sequence of gaps, each next term must be above the closure of the previous one. So this is a sort of proposition, or actually almost an exercise.
Okay, go ahead.
Do you see it now, or should I reshare?
It's working now. You can go ahead.
Okay. Yeah. All right. Look, so that's okay. So let's So this is an example of, there is no diversity here. All those, these are all those not semi-regular cuts. They all have cofinality omega, and pairs are all isomorphic to one another. Those are actually very interesting cuts, and they can be used for various constructions, but we are not getting a diversity here. There is uniformity. Okay, but now, so this is something that comes from Smorinsky's paper. He refers to, maybe Laurie remembers, but I couldn't check where actually it is, maybe actually in Laurie's thesis, 1977, that is from older work. It was well known that every model M, you can, into every countable non-standard model, you can embed continuum many models of PA satisfying continuum many different theories. You can embed them into as elementary cuts, not as elementary cuts, but as a cut into M. So there are continuum many theories of cuts, which are themselves models of PA, but with more care, you can actually embed all those models onto semi-regular initial segments of M, regardless whether M is recursitively saturated or not. So you get continuum many theories, not of pairs, just of those cuts. And then based on that, since there is the same construction, if you have an element that codes an ascending sequence of gaps, but now not of length omega, but length of I, where I is any given initial segment, so the arithmetic cofinality of this cut I in M is I, if I is semi-regular. And so because of that, I is definable in the pair. And since we have continuum many theories of the I, of the semi-regular cut I, this gives us continuum many theories of pairs for semi-regular I. But so I is semi-regular, but this K say I is not. Again, this is diversity below I sigma 1. This is a not semi-regular cut because the cofinality of it is not KIC, the cofinality of it is I. Okay, so so this is just, this proposition here is essentially the same thing, that we are below I sigma 1. All those cuts are models of B sigma 1 and not I sigma 1. Okay, look, and here is something, it's a cautionary tale. Smorinsky proved many interesting results, but he also stated several results that later turned out to be false. And always with some interesting comment about the proof that he omits for the reason one or the other. So in particular, I call it here a conjecture, but this is in one of those papers that I listed in the references. So Craig has this as a theorem. It's analog. This is definitely true, and I showed you on the pictures that if you have two ascending sequences of gaps of length omega, then this is true. Okay, that all those pairs are isomorphic. But Craig said, well, if you take any semi-regular cut, the same holds. But I'd like you to read, maybe I'll read it. Instead of proof, he has this comment of the theorem. We shall not give the proof here. It requires a special back and forth technique used to prove theorem 1.8, which is essentially something like this for omega instead of I. Like the proof of this latter theorem, it fits more naturally in 6. It's a paper that was published later, but this result is not there. There it will be modulo a small trick supplied by Kotlarski to handle a key difficulty, just another of several applications of a simple but moderately powerful tool. Here, without a reasonably leisurely digression explaining the method, it would give an undue impression of depth and or cleverness. So anyway, so this is an excuse for not giving a proof of the theorem, but it's a good
It's
thing.
so clever.
Maybe
I mean, so
bad
witty.
thing that Craig did not give. It's very witty. However, okay, the theorem is false. The conjecture is false. This is something that I was, and I came with it because I needed Craig's theorem, purported theorem, But before using it, I wanted actually to see how it's proved, and I couldn't. I tried to prove it, and I couldn't. And then I remember I met Jim at some conference somewhere, and we talked about it. And when we talked about it, we actually came up with this example here. So this is a joint work with Jim, but and so an example, and I think so I want to go over some details of this argument, how to construct these two cuts of cofinality I for a semi-regular cut I, such that not only non-isomorphic, but such that even the theories are different. And so it shows that there are some complexity here, the complexities that are hidden. And one of the sort of interesting aspects is that what's not visible at the first glance is that presence of truth definitions on recursively saturated models. And that helps, and this is part of the structure and sometimes becomes part of the theory of the pair. So M is a recursively saturated model, K is its elementary initial segment. So now we're looking at the supremum. So S of K will be the cut of K, supremum of those A's, such that there is something in the model, there is an element such that if I look at what this element codes on the submodel K, this will be a sigma E satisfaction class for K. So what this means that this set will satisfy Tarski's conditions of satisfaction formally written. So E could be a non-standard parameter here for sigma E formulas. Okay, so there could be K could, for example, have a full satisfaction class coded, and in this case, the supremum will be simply K. And if K is not recursively desaturated, then this supremum will be omega, because existence of those sigma E satisfaction classes for non-standard E implies recursive saturation. So for non-recursively saturated cuts, the supremum is omega. And then there could be other things in between. So to get the example, we do the following thing. We write a theory. So C and D are constant. We add new constants to the language, C and D. We add predicates for a semi-regular cut. We add predicates for those two elementary submodels, K1 and K2, and we list the requirements. So those C and D, well, I forgot to, this is a typo. What's missing here is I, but it's somehow covered by the second line. So C and D code ascending sequences of gaps. I is a semi-regular cut. Both those sequences are above I, and the length is at least covers I. And now this says that well, K1 is the supremum of Ci, where I is I, and K2 is supremum of Di, where I is I. So these are those ascending, the supremum of those, like on my picture, those models determined by these two sequences of length I. Okay, and now we want this S of K1 to be I, as large as possible. Well, not as large, but just I. And the other one we want to be greater than I. So if we get a model of this theory, and if you click on M, then this will be the example. This will be the K1 and K2 will have cofinality I. They will be of this form here, but the theories will be different, because one theory will say that the S of K1 is I, and the other say S of K2 is greater than I. Okay, so now how are we getting those two models? So first of all, M is recursively saturated. It has an inductive satisfaction class, but moreover, it has an inductive satisfaction class such that the pair is itself recursively saturated. So now we take D to be an ascending sequence of skies, of gaps, but in this structure, MS, it's a recursively saturated structure. So it's like M. It's a model of what's called PA stars. So this machinery of minimal types works, and we can get an ascending sequence of skies there, and we take the model that's determined by the sequence of skies. D codes the sequence of length omega, and there are ascending sequences of gaps in MS. So if I take, so this will be, if I take a restriction to S is a satisfaction class on M, if I take the restriction of S to K, because of speed of growth of the sequence, one can show that K2 together with this U is an elementary substructure of MS. So in particular, U is a non-standard inductive satisfaction class for K2. And because of that, S of K2 is non-standard. So that's how we're getting this K2. And now the question is, how are we getting K1? So now K2 is already here. And I take first, this is an auxiliary K. I take some short model. I take any non-standard element, and I take a supremum of this column closure of A. So this is a shortcut. And because it's short, it's not recursively saturated. And because it's not recursively saturated, S of K will be, well, so the two things that happen. K has cofinarity omega. So this I here for S is exactly omega, and its S of it is also omega because it takes no non-standard satisfaction classes at all. Okay, so now the claim is that if I take any finite fragment of this theory T, this structure where M is fixed, K2 and C and D are fixed, and K is this model here. It's a model of T0 because the only thing that's missing here, the difference between T0 and T is T requires, well, it's all hidden. Where is it hidden? Oh, here. The point is that to state this is an infinitely many statements. You say that for any, so to say that C is an ascending sequence of gaps, you say that for any term, the next term is larger than the values of column terms on the previous one for every column term. And so it's an infinite list of requirements, one for each column term T. If you take a finite fragment, there will be only finitely many of those requirements, and they can easily be satisfied in K. So it's easy to verify that this structure is a model of T0. And now we appeal to chronic, well, just to resplendency. I have a theory of an expansion of a model that's consistent, and it's a recursive set of requirements. So the model itself is expandable to the theory. And now this M, K1, K2, C, and D are a model of T. And that's the example that is a counterexample to Smorinsky's conjecture. So I think it's nice. It's elegant. It has all kinds of elements in it, but it shows that there is some hidden structure that so far we've been looking only at cuts and some suprema or infima of certain sequences of elements. But there is more in the structure that meets the eye, because there is some second order structure on the cut that somehow recovered, that can be recovered from the knowledge about the pair. So it's just some things that's slightly more complicated than it seemed at the beginning. Okay, so now I said that we can get this diversity of different cuts either at the low end, so that's below I sigma 1, or at the high end when you go all the way up to strength, which is the same thing as arithmetic comprehension. Nothing for fragments, and that is because, again, because we're using satisfaction classes. So this is something I observed a long time ago, and there are different ways of seeing it. That you're on a fixed model, you can not only have inductive satisfaction classes, and not only you get continue many of them, but you can get continue many theories of satisfaction classes. It's completely undetermined what the theory is, complete theory of the satisfaction class is. There are continue many choices. And now to get many non-isomorphic pairs MK, where K is an elementary cut that is strong, then you do something like this. For you have continue many different continue many satisfaction classes that are pairwise non-elementarily equivalent. For each of them, there is an elementary and extension in which this class is coded. And now this is a simple counting argument that, well, so you have this end extension. So MS is isomorphic to M. So this situation is mirrored by M itself and some cut of M that looks like this pair MS. Now we're looking at the pair MS-M, but this pair MS-M is isomorphic to the pair MKS. For some K, there's a cut of M, and a counting argument. Okay, this is something bad here. And so you do the counting argument, and you're done. So it's a simple argument. Okay. And now this question here, I probably have to skip because, oh, no, I don't skip it at all. No, this is, it seems that because, well, this argument, even though I'm using satisfaction classes that are not elementarily equivalent, what I get at the end is just non-isomorphic pairs. And they are non-isomorphic because you have those countable systems, and and you have uncountably many things in them, so there must be uncountably many non-isomorphic structures among them. But how many different theories are there? It seems that we're very close to saying that this is the same, but I just couldn't prove it. I can prove it in the case when that this continuum in the case of true arithmetic, because then you can use full inductive satisfaction classes and the argument works. But in general, this is, at least it's open to me. I couldn't recall if this is something that's been done somewhere. So this seems to be an open question.
Roman, can I ask you a question?
Okay, but here is something. Yes.
Are those in that corollary right there? Are those can those pairs be balanced? That when K is strong and M.
Erin, no. So we're back to the countable case. In the countable case, they are all aleph 0, 0. So those are to the consolidated case. Here, those distinctions don't matter. Everything's countable.
Okay.
Good. Okay, so I was asking this sort of simple question, So if, well, we can do things at the low end, we can do things at the high end. So how about somewhere in the middle? Okay, so what about this collection of pairs where K is semi-regular, but not more than semi-regular? Or there are many similar questions that you can ask at various levels of this arithmetic hierarchy. So an example was given by Lawrence, Tin-Lock Wong, that there are at least, in this family, there are at least 2 non-isomorphic pairs. And we know that we can do it in the case when the model is actually arithmetically saturated. So the way it's done is this. So we assume that M is arithmetically saturated. Arithmetically saturated means that the standard system is closed under arithmetic definability. It's a model of ACA0. So those are models that are arithmetically saturated. And so I will show you those K and L that are both semi-regular and not regular, but the pairs are not isomorphic. How are we doing this? So this will be by using some heavy artillery. So this is from a paper by Lawrence and Richard Kay. They defined genericity of cuts, and I will not define this for you. This would take about probably half an hour just to define the notion, because this genericity of cuts is defined in terms of some topology on the set of cuts in a model, and in a recursively saturated model, and taking into account actions of automorphisms and all kinds of things. But anyway, those generic cuts exist. The criteria are something is a generic cut if any 2 generic cuts are conjugate. So there is an automorphism that carries one to the other, but you also you want to have many of them. So you in this topology that they define, they want to have the set of generic cuts to be comeager, and they define those cuts, and they have cuts which satisfy those 2 requirements. And then they prove that it works in any recursively saturated model for cuts, just for cuts, but to get elementary generic cuts, you have to go to arithmetic saturation, and then they exist. So I can say, let K be an elementary generic cut. To here, this assumption of arithmetic saturation is used. And then Wong and K prove that any generic cut is semi-regular and not regular, exactly the way we want. So this genericity sits somewhere at this level. Okay, so we have one pair. So now we take another pair. So we simply take a pair ML, where L is semi-regular but not regular. This is a first order property of the cut, such that the pair is recursively saturated. And now we use another result of Wong and K to say that generics are fine, except the pair is not recursively saturated. So those pairs with elementary generic cut necessarily are not recursively saturated, and that's how you get to non-isomorphic models, and that's the state of the art. That's the best we can do so far about this question. I think this is a good question, but it would require some more insight into what possibly can be done. Many questions? Nope. Okay, so
I have a question.
The clock now is I have a few minutes. So
I have a question.
Okay.
Question. Yeah, throughout
Yes, yes,
here, we're
yes.
seeing recursively saturated models playing a role. Now, as I remember it, the key property in my day of recursively saturated models was that they were resplendent.
Exactly.
They could be expanded. Is that playing a role? Is that property what's key to the constant sort of reappearance of recursive saturation in these arguments?
Yes.
Thank you.
Yeah, no. I was just going to quickly flipping. So, for example, in this example here, that's absolutely crucial. At the end, I appear to resplendence to get an example, but also this is resplendence is behind the theory where it says, well, the world of cuts is vast. There is topology on the set of cuts. You continue many. There are limits. This whole theory. Now and then, you have to appeal to resplendence to say, oh, the type of the cut of this type exists, type of that cut exists. So it's behind everywhere. Recursive saturation is used for back and forth arguments, but everything else seems to be resplendent.
I mean, the Ehrenfeucht Fra-Issei arguments.
In Ehrenfeucht, that's more recursive saturation than resplendence, I would say.
Yeah, Fra-Issei was from Algeria, from Alger in Algeria. So he might actually rate as the greatest logician from North Africa since Philo of Alexandria.
Well, we should make a case. I know his name is all over. You know, whenever there are no other arguments when you have to compare two structures and show that they're elementary equivalent, if they actually are. Then you have to use his games, and that's brilliant. And that's other things as well. But look, so I don't have much time, but I wanted to cover this today. And that's because Alf asked a question here, and this is sort of also in the back somehow, various notions of genericity. And so in this case, it came up with Wong and Kay, and they worked hard to actually come up with a very plausible notion of genericity, although one can argue whether this is the right notion or not. I defined something, this is my early days, a very simple notion of, I wouldn't say necessarily tameness, but freeness of a cut. And it's a very simple definition. And it can apply to just an arbitrary subset as well. And I said that a cut is free if it has this property. If you take any two elements in the cut, if they have the same type, then the types remain the same after you throw in the predicate for the cut. And you can say, well, why are we restricting this to just to A and B in I? Maybe there could be also any A and B above I, but then in case of arithmetic, there wouldn't be any free cuts. You can only go because of the coding power. So this really makes sense really for elementary cuts and for for elements inside a cut. And the question is, do they exist? And then one thinks about it for a while, and there are various proofs. So if you take any gap, then infimum of the gap is free. And and we know that there are, because of that, then there will be non-isomorphic, infinitely many non-isomorphic free cuts of that form. And also all those models that are suprema of coded sequences of increasing, ascending sequence of gaps of length omega, they are also free. So there are examples of free cuts. And here it is. Kay and Wong proved that their generics are also free. So they have this nice notion of freeness. So that shows that they're actually more than Aleph. Well, it doesn't prove that they're more than Aleph 0. So it's Aleph 0 plus 1, because all generic cuts are isomorphic one another. They all conjugate. So we have 3 types of generics. Well, there is one type. All these are isomorphic as pairs. Then we have countably many non-isomorphic, potentially non-isomorphic pairs like this. And then we have one more, generic. But my original question, and because I sort of thought this was a nice, it was needed for some constructions of omega 1, like would be handy. Have cut, elementary cut that's free, but at the same time, I wanted the pair to be recursively saturated. And I couldn't decide if there are cuts like that. Kay and Wong showed that their generic cuts do not have that property. And it's still open whether cuts like that exist. And it would be nice to decide it at some point. So let's see. Look, so now I am at the part 4, where the real talk begins. So far, it was just a preliminaries and some old results. And what I really wanted to talk about is what's in our joint paper with Jim. And what I will say that last week when Attar introduced me, he said that I'm a godfather of this seminar. And since it is really so, if it's really so, then I'll say that I will talk about it one more time next week. So part 4 will be next week.
That sounds great. Let's clap. Using our emojis. Do we have questions?
I had a question.
Uh-huh.
Back to that question about the number of theories at the isomorphism of balanced pairs. What's the possibilities? I mean, could it just be one? I mean, what do you think? Like, is it?
Well,
are there going to be a lot of them, or?
Look. So I don't really have a good intuition. No, this is a small and informal seminar, and we don't have too many foreign participants. So, because I don't want to embarrass Jim. Jim had early versions of his paper, and I actually, when I was preparing these notes, I used an old version, which turned out to be the wrong version of the paper to look at, because in the earlier versions of paper, Jim proved many results that turned out to be false. So in particular, he proved that all balanced pairs are isomorphic.
Oh.
Oh, no, they're actually they're elementary equivalent to one another. No, they couldn't have. No, he proved exactly this: that if a pair is balanced, if you have 2 balanced pairs, and if they're elementarily equivalent, then they are isomorphic. And there was a longer, complicated proof, but at the end it didn't quite work, because this is simply not so. But look, so we know that we have continuum many non-isomorphic balanced pairs, because we have continuum many theories of those pairs. And so I remember when I was asking Shala, if he has some ideas what can be done. Look, potentially you can have 2 to the kappa many. Why not? And but it's very hard to see what the difference within those cuts would be. And so, for example, to get some hand on it, I was thinking, how do you make a balanced pair that's not saturated itself? Okay, because you have you have well, in the argument that from different theories you get different non-isomorphic pairs, you really get different non-elementarily equivalent pairs by going to a saturated. You're looking at saturated pairs, and then gives you continuum many non-isomorphic because they are actually get continuum many non-elementarily equivalent ones. So how can one construct a pair that's balanced and not saturated? And I don't know how to do it, and Jim didn't know at the time when he was thinking about it. So there are all kinds of strange things about it. Probably requires some insight into the nature of those saturated models that sometimes deceive you.
Okay, that's interesting. Okay.
A lot of results talk about there being 2 to the Aleph 0, instances of things. Why does the continuum hypothesis never enter into it?
Excellent question. And probably because we're doing things that are sort of low level and rather naive. There is something that I discussed with Jim a month ago, where a continuum hypothesis actually entered, and we still wonder why. There was something about, actually related to your previous question, something about resplendence of a certain omega-1 limit of elementary or final extensions that is not resplendent under the assumption of continuum hypothesis, and we don't know what happens if we don't. So, but though we're not really using, well, what I am not using any sophisticated model theory. This model theory that we're using here is at the level of sort of taking unions of omega chains, and resplendence is used now and then, and all of that. I haven't seen any independence at this level. Jim has results about kappa-like models for larger cardinalities, and there, once you start doing things with larger cardinalities, all kind of theoretic things come up. So, but not at the level of countable models and their sort of omega-1 limits.
Thank you.
Oh no, I said, but since you asked, there is one thing that actually Corey gave a talk about it not so long ago. There is one mystery here where we have this constructions of omega-1 like rather classless models, recursively desaturated, that use sort of high-level diamond elimination techniques. And the question is, well, can you construct a model like that? We know that they exist, the existence theorem in ZFC, but we wonder, well, can one actually provide an explicit construction of such a model? Again, so this is like a sort of low level of possible independence, but you have to go to omega-1 to even begin.
Oh, that definition of free reminds me of independence, and I'm teaching my students independence. It just the definite. I like that definition. It just reminds me of independence. The definition of independence.
Well, I like this definition because it's simple. It's really very simple.
Like conditional probability.
No.
Very strong property.
Right. Right. And however, strong cuts do not have it. Or even super strong. So that one could think that the stronger the cut, sort of the more like free it would become, but it turns out to be false. Strength does not imply freeness.
Roman, if you add in, so you see there's some sort of picture that's somewhat clear on the weak ends and on the very strong ends, but if you go even stronger, does the picture get even clearer after that? Or if you go to sort of sort of models of stronger theories than ACA not.
Well, but then you see, but because those theories come up only because they somehow correspond to the levels of first order.
Mhm.
You know, well, there is this hierarchy of that somehow the first order properties of cats translate to those second order theories of families of coded subsets. And so that was more or less the motivation. We could just stay at the combinatorial level of those definitions. And I'm not sure if those things stronger than AC0 correspond to anything that we can put a finger on in this case. But perhaps, because so what comes to mind is transplendence. So but I haven't looked at that. I haven't looked at transplendent pairs, and this is the work of Engström and Kay. So maybe there is something there.
Thanks.
Roman, this goes way back, but when you defined semi-regularity, and regularity and so forth in terms of I sigma 1 and D sigma 2, way back, there was something that was bugging me about that's yes, this slide. I is semi-regular if and only if, should that two-parted structure here be I, comma, you do mean M, comma, code M over I?
You mean part one?
Yeah, well, all those parts actually. You're looking at M with, you're looking at M with a collection of coded subsets.
Right. So these are subsets of I,
Yes.
coded in M. That's the notation that we. Right.
But the first order part should be I, right?
Yeah.
The first order part should be I, essentially.
Oh, right. No, you're absolutely right. No, this is all cutting and pasting. All of those things. This M is definitely M here, read I.
Okay. Relief.
Yeah, throughout. This is just bad. Yeah. I made a typo once and then I was just copying and pasting. So that's awful. Right. Thank you. Yeah,
very keen,
M
Maury,
is
very
I.
keen.
I've been trying to think, would it work with M there, but you don't have any induction at all with M there? Because
Oh, no, with M it's a disaster. Right.
yes, okay.
Any other questions? Okay, let's thank Roman again, and so I guess we'll be seeing you again next week. You'll be yeah. So hopefully everyone can rejoin us then.